Hey everyone, Hal here. In this video, we're going to explore a question that is fundamental to quantum computing. The question I am referring to is how can we know that future quantum computers will outperform the fastest supercomputers? Currently, there's an arms race between countries to build faster and more powerful supercomputing platforms. So what is the difference then between building a functional quantum computer and improving current supercomputers? Well, that's the trick here. When we are talking about the speed of quantum computers, we aren't talking about speed, at least not in the absolute sense. Instead, we are talking about something called computational complexity. What makes quantum computing so powerful is that it allows us to reduce the computational complexity of certain problems, sometimes significantly. In this video, we're going to dive into what this sentence means and what its implications are for the applications and power of quantum computing. And if you enjoyed this video, be sure to like and subscribe so you don't miss all of our upcoming videos on quantum computing and quantum physics. All right, let's get into it. So, firstly, what is computational complexity? Well, when analyzing an arbitrary algorithm, for example, something like sorting an array of numbers or searching through a book for keywords, we can determine something called the complexity of the algorithm. The complexity is a way of describing the number of steps required to find the solution. So let's look at a few examples. If, for example, we have an array of length n, and we write a for loop which loops through every value in that array, this for loop is going to execute n times. In this case, we can say that the big O notation for this algorithm is O of n. This notation is how computational complexity is expressed. It is always written as a function of n, where n is the length of the input to the algorithm. In this case, n is the length of our array, but n can have numerous meanings depending on the problem being solved. Another example would be the case of a nested for loop, where each for loop goes through the entire array. In this case, the inner for loop is going to be executed n times, and each time it itself will execute n times. Or in other words, there will be n times n operations. So in this situation, our big O notation will be O of n times n, or O of n squared. As an algorithm gets more complicated, the equation that governs the number of computational steps required for completion will likewise grow. That is why when we are stating the big O notation of an algorithm, we drop the smaller terms in the equation. What I mean by this is, let's say for some input of length n, an algorithm is going to perform 2n cubed plus 5n squared plus n plus log of n steps. In big O notation, we would say that this algorithm is O of n cubed. We drop the coefficient and smaller terms because the main goal of big O notation is not to provide an equation for the number of computational steps, but instead to help us understand the way the number of computational steps increases as n goes to infinity. In a real implementation of the algorithm, these terms could be really important. For example, an O of n cubed algorithm could be faster than an O of n squared algorithm depending on those dropped terms. But as n approaches infinity, this will change. So what is the point of this? Well, big O notation is useful for two reasons. Firstly, it allows us an insight into the performance of an algorithm. Secondly, it allows us to compare the speed of different algorithms independent of the hardware they are ran on, by comparing the computational complexity of each algorithm. For example, if your friend has a computer that is much faster than yours and you both have created an algorithm for solving some problem, it is not going to be useful to compare the run times of your algorithms to understand who made the better one. Because of the differences in hardware, these values become meaningless. However, the big O notation for each algorithm will be the same on each computer, so it provides a framework for comparing them. An important concept that emanated from the idea of big O notation is that of complexity classes, which are just ways of grouping algorithms based off of their computational complexity. There are a million different complexity classes. I'll put a link in the description to a wiki dedicated to cataloging them, but in the context of quantum computing, there are two that are very important. These two are P and NP. You may have heard of the famous P equals NP problem. This problem is referring to these two complexity classes and is asking whether all problems in NP actually are in P. What is known is that any algorithm in P is also in NP. And most computer scientists suspect that P and NP are not equal. However, it has yet to be proven. In fact, if you are able to prove it, there's a $1 million reward. So what are these two classes? Well, P is a class of algorithms that can be solved in polynomial time, or in other words, whose big O is polynomial. For example, O of n squared or O of n cubed. NP, or non-deterministic polynomial, refers to algorithms which can be solved in polynomial time on a non-deterministic Turing machine. What this actually means is a bit complicated. However, all you need to understand is this. Algorithms in NP which are not in P are generally exponential time algorithms. Like, for example, factoring a number, which for the simplest algorithm is O of 2 to the n. Again, this isn't a rigorous definition of NP, but it does suffice for now. This distinction between problems in P and NP is important when you consider the ways in their different O notations are going to behave as n increases significantly. Problems which are polynomial time are going to perform much, much better as n goes to infinity than problems which are exponential. And for this reason, problems with exponential time algorithms tend to be much, much more difficult for classical computers to solve. Okay, so with this established, let's go back to that example where I mentioned factoring and how its big O notation was 2 to the n. So due to this fact that factoring is exponential time, it quickly becomes an extremely time-consuming task to compute as we increase the size of the number we wish to factor. For this reason, encryption algorithms like RSA rely on the difficulty of factoring to encrypt information. In 1994, Peter Shor developed an algorithm that almost overnight created the field of quantum computing. Shor's algorithm is a method for factoring a number in polynomial time on a quantum computer. This was an amazing idea, but the implications of this fact were even more significant. This showed that quantum computers were able to do something previously not thought possible, and it really got people wondering about what other algorithms could be sped up by quantum computers. What this means is that as the size of the number you are trying to factor grows, the number of steps you have to perform to factor it increases at a much slower rate. So for large enough numbers, this difference will become massive, allowing you to factor big numbers much faster. And since the security of the internet relies on the difficulty of factoring, this is the reason that many people are concerned about the risk of quantum computers could pose to encryption. However, as it stands right now, this is a distant danger. Current quantum computers are very far from the size needed to factor the large numbers used in RSA. Furthermore, there's research indicating that there are likely quantum secure encryption protocols, so I wouldn't worry about this just yet. Interesting, quantum computers might also provide the solution to this problem, thanks to something called quantum key distribution, which is a method for perfectly encrypting something with a quantum computer. Make sure you hit that subscribe button so you don't miss our upcoming video on quantum key distribution. So this is what people mean when they say that quantum computers are faster than classical ones. It's not a statement about absolute speed, but instead a statement referring to the ability of quantum computers to change the complexity of algorithms. Which in the end is a much, much bigger deal, because if it were just speed, we could always build bigger computers. But instead, a quantum computer is able to accomplish something completely different. On the other hand, though, this also means that quantum computers are not going to be faster at every problem. In fact, for problems where there is no change to the computational complexity, they will likely be slower. Instead, in order to gain a speed up for a problem, you must discover an algorithm that uses quantum mechanical properties to compute the problem with a more advantageous big O notation. To me, the most interesting part of this whole discussion is the fact that we still don't really understand why quantum computers have such different computational properties. The existence of this exponential speedup that certain quantum algorithms like Shor's are able to achieve implies that there is something very fundamental in theoretical computer science that is not understood about quantum computing. Providing an explanation for the reason behind this speedup would be an immense accomplishment, one that would surely impact large sections of the field of theoretical computer science. And with that, I want to finish up this video. Thank you guys so much for watching. I hope you enjoyed my explanation today. And if you did, be sure to subscribe and hit that like button for more quantum computing videos in the future. Thank you.